Dear students, welcome to the tutorial number 1 of decision support and uncertainty. My name is Pavlo Glushko, and I will be your supervisor and tutor in this semester. With Professor Koberstein, we will help you in the journey in stochastic optimization. And today's tutorial, I would like to start from some formalities and explanations about the course. Probably at the time of watching this course, you already attended the online lecture, which was provided by Professor Koberstein, but still I will explain some things so that you don't have any questions. And the main communication channel for this course is Moodle. So of course you need to have access to Moodle. And then when you go to the course, you already have several statements about the course. So one of the most important things is that this course is completely online in time of Corona. You can take it and participate in it from any part of the world whenever you are, as long as you have access to Moodle. Lectures, as you might have already experienced, they are online and they are synchronous. So it means that they're live and you can state questions just during the lectures. They take place every Thursday. Here you have time from 10 to 1:30. And the tutorials, we decided to do them in this format, in the format of the recorded videos, so that you can stop something, go back. The tutorials, they will be followed by the questions and answers session, which will take place every Monday from 10 to 1:30. So if you have some questions which you want to ask, you can ask them for the tutorial on the following Monday during the questions and answers session. Also, if you have questions, you can state them in the forum, questions and answers, so you don't need to wait until the session. And maybe, if it's a short question, why do you need to state it online? Yes, and I would encourage you to put all the questions in the forum and not write in us email, because then your colleagues, they can also see your questions, and maybe they can even answer some of your questions for related to the contents, and then we don't need to answer several questions, same question several times. So please use the discussion forum. Of course, if you have some personal question, like about your situation, study situation, about your grades, then feel free to write an email. My email, it's, as it always happens, it's my surname, Glushko, and then at Europa Unity app. Now about the exam, it will be also online and will take place in Moodle, so it will be online exam. We never did online exam for this course, but what I can say that exam will be based on the contents of tutorials and lectures, and practical questions in the exams, they will be similar to the questions in tutorials. Of course, questions will be in exam will be often smaller and shorter, because it's not possible for you to answer such a big questions. You have a limited time. Exam will take like 120 minutes, so 2 hours. You need, as always, to register to it, to participate. Then about the formalities, also, yes, you need to have a Windows machine, Windows computer, because we will use later in the tutorials MPL model and system, and this system, unfortunately, it's not developed for other operation systems except Windows. Yes, exam I already told you about. And yes, so we will have 6 weeks and therefore 6 online lectures, but we will have only 5 tutorials. So on every week, tutorial will be related to the lecture of the current week. But we will not have any tutorial for the last lecture. This last lecture, it will be on the week 6, and you need to prepare to the exam. So last lecture, it will be more theoretical, and you might have questions from the lecture, but they will be most probably theoretical, since you don't have any tutorial. Here is the draft of the topics. I think you have some of them already in the lectures. Maybe we will change something due to the situation. All right, here I might also change something for the tutorial. Yes, and for every tutorial you will get an exercise sheet as you have now with several exercises, and every exercise that can be divided into several bullet points. For every exercise you get the solution. So you get the record of how it was solved during the tutorial, as I will do it now, and then you will also get the solution where everything is written uh, like in a very clear way. So if you don't understand something from my writing, you can always take it from the solution. This is basically it, and it was everything from the formalities. Now we can start the tutorial. In today's tutorial, we have 3 exercises. These exercises are related to the linear optimization, so it's a warm-up. And on today's tutorial, we just want to introduce you to the linear optimization if you never worked with that before. Linear optimization is not the focus of this course, but it's a quite important knowledge to understand the concepts in the future. If you already know what it is, maybe you can even skip today's tutorial. But if not, it's a very nice way to understand the main concepts. So let's start with the first problem. You can maybe stop video and read it. And so we have the company that produces 2 types of paint, exterior and interior paint. For every product, we know the demand, daily demand, and also we know the profit from the ton of every product. It's 5,000 and 4,000 euro. And then to produce every product, so to get this profit, we need to use some materials. The amount of these materials is provided in this table. So what do we have here? We use 2 materials for exterior and interior paint, material 1 and material 2. For every ton of paint, of exterior paint, we need 6 tons of material 1, and for every ton of interior paint, we need 4 tons of this material. And then the number of tons that we have per day for this material is 30. The same idea, but different numbers we have for material 2. So we have some usage of this material for exterior paint, for interior paint, and then we have the available amount of this paint, which is 6. Yes, and then also in this table, again, in the tabular format, we have the profit per ton and daily demand. So basically here is restated what was mentioned before. Now, our task basically for this business situation is to find out what are the production quantities that yield the highest profit. So, to simplify it even, the question is how much of every product we should produce, of every paint, to have the highest possible profit in this situation. And then we have, since it's an exercise, several subtasks. We'll start from the first one. So we are asked to identify the basic components of the problem from the point of view of linear optimization. So we want to take this textual description and somehow to transform it to the linear optimization problem or LP model. Every LP model it has several objects or several components, and they're mentioned here: decision variables, parameters, objective function, constraints. Yes, and then when we know them, we can basically put them together and formulate this model, linear optimization model. So let's start. So, and first what we start from are the decision variables. From the name, you can guess that decision variables, it's something what we are asked to decide. Variables, it's some quantities which we can change as we want. Of course, we want to change these quantities in a way that we attain our aim. Our aim is to get the highest profit as possible. And so when we look And the decision variables, what are actually we are asked to decide. Let's look at this last question, and it said that it asks us what are the production quantities that yield the highest profit. So basically, we're asked to decide about the production quantities. Production quantities of two products. How much of every product do we want to produce? That are the decision variables. These are decision variables in words. Now, since LP it's linear optimization or mathematical optimization, we need to provide some, always formulate the concepts from the real life in the way of, in the form of numbers or variables. And these decision variables are quantities that we don't know that, but which we want to decide. Therefore, we normally use letters of them, somehow depict them mathematically. So I will write that we have here decision variables, and they are the production quantities of interior and exterior paint. I will denote them with X. It's quite oftenly used X. X1 will be production quantity for interior paint, or let's start exterior paint because it always goes first. Exterior paint, and X2 are production quantity of interior paint. We could also have more like index 3, X3 if we have 3 products, X4, and so on. Instead of X, we could use any other basically letter. Like Y or Z are often used. And instead of numerical indexes, we could use letters or even several letters. So I could name this first variable not x1 but xx. It's not necessary. Then let's go to the parameters. I will put some red color for them. Parameters. Parameters is all the input information which we are given. Normally this is the numerical input information because we talk here about mathematical models. And if I look now in my textual formulation, what basically parameters are all numbers that are provided to me. And this, what are they? Is the demand. Yes, it's 4 tons and 2 tons, daily demand. So say that it's demand, 4 tons and 2 tons. Then it's profit per 1 ton of product. It's 5,000 euro and 4,000 euro. And these numbers or this data, and then the data of material requirements, it's summed up, summarized in the table. So all this table, it's also parameters. So my parameters in this problem is all the provided data. I will not rewrite it again with all the numbers that I have. I will just say that it's daily demand, quantities, and then profit, and requirements. All these numbers which were given. Now, next component is the objective function. Let's use I will use again blue. So objective function, basically what is this? Objective, it's clear, it's the aim which we want to attain, and we want here to maximize our profit. And function, so function is basically the mathematical representation of our aim, right? So our objective, we want to get this highest profit as possible. Objective. To get the highest profit as possible, in one word, we can say that we want to maximize this profit. So it's maximization. I will just use short max. would be also minimization if, for example, we would like to minimize our costs. So if you would like to make a decision about production quantities or any other quantities that would minimize our costs. But in this problem, we are asked to find as production quantities that guarantee the highest possible profit. And now, yes, I can write max profit. But since we talk about the mathematical optimization, to write it down in this way, it's not enough. We need somehow to represent the profit with numbers and maybe decision variables, so letters, in the mathematical way. So how can I write down profit in mathematical way? So how do I calculate this profit? Basically, I know the profit per every ton of the product, which is 5,000 and 4,000 per every ton of produced and sold product. And this quantity is how much of every product I produce and sell, I decide by myself, x1 and x2. So if I want to represent my profit mathematically, I can write it down in this way. So first it's profit per 1 ton of the first product, 5,000, multiplied by the number of first product, tons of first product that I produce. And this amount is x1. I should decide it. So instead of x1, when I make a decision, it will be some real number. But currently it's x1. And then I add here the profit from the second product, which is 4,000 per ton of the second product of the second paint, multiplied by x2. Yeah, of course, I don't need to write this multiplication sign. And also, it's some mathematical convention that we write the coefficient. So 5,000 and 4,000, these data elements, they are called coefficients. And x1 and x2, of course, is decision variables, right? And then this part, this is basically the function, our, yes, it's the function, the mathematical function. And max, it's our objective which we want to do with this function. Therefore, it's called all together as objective function. So the last element, and probably the most complicated one, these are constraints. So if I look at this objective function and I am asked to maximize it, basically I could set this x1 and x2 to any values, like 2 million, 2 millions, 3 millions, and so on. So I would increase my objective to any amounts they want, and it wouldn't have any limit. But unfortunately, in real life, we always have something that limits our possibilities. And in this problem, we have something like that as well. And this what limits our, so to say, decision space. It's called constraint. So I will write down constraints. And these are some facts and statements and elements of real situations that limit the amount of products which we can produce. So what are the things? First of all, demand is mentioned. So the daily demand, what basically it means, or how can we interpret it? So if we have the daily demand for the exterior paint, 4 tons, we could interpret it basically in 2 different ways. The first interpretation that we will use in today for this problem, it means that if our demand is 4 tons and we will produce 5 tons, we will be able still only to sell 4 tons. And from the last ton of the paint, from the 5th ton of the paint, we will not get any profit. If we don't get any profit, it means that we will get some or experience some costs, but we will not be able even to sell it. So it makes completely no sense for us to produce more than 4 tons of exterior paint per day, because we will not able to sell it and get profit. Same for the interior paint. the same idea, but just another number. That the daily demand is 2 tons, so we don't want to produce, we will not produce more than 2 tons of this paint. In some other problems, you might be mentioned something like, if you produce more, you can store it in your warehouse, or you can sell it at some lower price. But in this problem, we just have the textual description that we have, and nothing is mentioned about that, and we cannot, so to say, use our fantasy and add whatever we want. And this is the interpretation that we will use. Another interpretation in some problems is that if we have demand of 4 tons for the paint, it means that we are forced to satisfy this demand. So we must produce the paint for all the customers that we have. But this requirement somehow it's not mentioned in the description. So we will use the first interpretation, meaning that we don't want to produce more paint than demand. Now, how do we formulate it? We want to formulate it mathematically. You see how we formulated our objective, so our constraints, they should look something like that. Let's first formulate the constraint, demand constraint for the exterior paint. So what we want to say? We want to say that the amount that we produce, so amount that we produce is basically x of the exterior paint, so x1. It cannot be more than the demand, right? So we can say that it should be less or equal than the demand, and demand is 4. So x1 is lesser equal than 4. In the same way, we can formulate the demand for the second paint. For the interior paint, x2 is less or equal than, I guess, 2, right? 2. And these two are demand constraints. It's important to know that in doing your optimization, all constraints like look similar to this one. So it has a right-hand side, or right-hand side is of course here, left-hand side, and the sign between them. This sign, it can be lesser equal inequality, more equal inequality, so lesser equal inequality, more equal inequality, or equal, which is the inequality, it's not inequality. In the constraints, we can never use more equal strict, more, we can never use strict less or strict more. It's related to the nature how we solve this problem. But you should remember that these guys, you can never use them. And this what you basically use for constraints. Now, what other constraints do we have? So our demand constraints now. Let's check. So it says that to produce any paint, we utilize some materials. We have 2 materials, and these materials are also scarce. So every material, it has some amount, and so we cannot use more of these materials that we have to produce the paint. So basically, how we formulate the material constraints, and we will focus now on the first material. The logic is quite similar as was here. We want to say that the amount of material 1 that we use, so usage of material 1, it should be for the paint production. It should be more or equal than what we have of this material, the available amount. An available amount, we know exact number for that, it's 30. For the material 1, we are provided that 30. So now the question is, how do we find the usage of material 1? As I said, we use it, as it's mentioned in the problem, to produce products. We have 2 products, x1 and x2. So mean that usage of material 1, basically it's what we use for exterior paint plus what we use for the production interior paint. Because there are no other products for the production of which we might use this material one. And here is less or equal, because if our usage is less than 30, it's also right. Maybe we don't even need to use all the materials that we have. Now, how do we calculate the use of material 1 for production of exterior point? So now we concentrate on this thing here. We know that from the table that for every ton of exterior paint which we produce, we use 6 tons of material 1, right? And the amount of exterior paint that we produce, we decided by ourselves, but in mathematical formulation, we use x1 for that. So the quantity of material 1 that we use for the production of exterior point is equal to 6. The usage, the requirement of material for every ton of exterior paint multiplied by x1, which is the production quantity of that paint. This first part usage of exterior point we find out it now, plus usage for the interior paint. Let's again look at the table, and we see that for the idea is exactly the same. For every ton of interior paint that we produce, we need 4 tons of material 1. So I just substitute here coefficient 6 with coefficient 4, because it's the usage of material 1 for the interior paint. And here I instead of x1 I put x2, because this is the production of interior paint. And this sum, it should be less or equal to 30. So this is the material one constraint. Now I will try to make it look a bit more neat, because now it has too much things going on here. This was the constraint for material 1. And now try by yourself, you can stop the video, to find the constraint for the material 2 in the same way. Okay, so how do we do it for the material 2? Material 2. So the usage again of material 2, it should be less or equal to the available amount of this material 2. The available amount we have in the table, it's 6. Yeah. 6 tons we have daily of this material. Good, now we need some mathematical formula for the usage of material 2. And use of material 2, we use this material to produce exterior and interior paint. How much of material 2 we use for the exterior paint? We look again at the table. We see that for every ton of production of exterior paint, we use 1 ton of material 1. How many tons of exterior paint do we produce? We decided by ourselves, its decision variable x1. So I can write down that usage of material 2 for the production of exterior paint is equal to 1 x1. Here I could omit this 1, because if I don't write it, it's still clear that x1 has a coefficient 1, but I will include it. And now the same, we need to find out for the interior paint for the second product. Again, I look at the table and it's 2. 2 tons of material 2 I use for every ton of interior paint. So I write down 2x2. And these are our material requirements constraints. You can see that every row corresponds to some material, to material 1, to material 2. If we would have third material, the idea would be exactly the same. We would like have again some requirements of the material for every product. Then you also can see that in the left-hand side, if you try, you will see something like a columns. Every column is related to every product. So first column, it's always product 1, exterior paint, and its coefficients. Second column, it's interior paint and coefficients. And coefficients here, these are the material requirements of every material for every product. Now we did the demand constraints and material constraints. Now you can think what other constraints would we need, or maybe not constraints at all. All right, so the last constraints that we have in this problem, they are not so intuitive for the human beings, but they are quite important when we put our problem in the machine, in the computer, so to say. We need to say that we cannot produce the negative amounts of products. All right, because we don't mention it anywhere, and of course it's not mentioned in the description because for the human beings it's clear your production it cannot be negative. But from the mathematical point of view and from algorithmical for the computer, we need to say that this x1 and x2, our decision variables, they should be always the positive numbers, or they should be non-negative numbers. So we just say that x1 is more or equal to 0. It can be equal to 0 if we decide not to produce first paint at all, which we can do. And then x2 is also more or equal to 0. And these are non-negativity constraints. These were all the constraints, and with the constraints we also defined all the elements of LP model. So we defined the decision variables, which are production quantities, and we denoted them with letters x1 and x2. These are parameters. I didn't write them here explicitly, but these are basically all the numbers that are provided in the actual description for our business case. This is the objective function. Objective function is maximization, or it can be minimization of some mathematical function. This function here, it represents our profit, but it could represent basically anything in the way of coefficients and decision variables. And there are some, but it could be here not only some, but minus can be as well. And then constraints. Constraints, it's something what limits our decision space, which limits the amount of the objective function. And we had constraints which are demand constraints, material constraints, and non-negativity constraints, which are most often by default, so to say, present in any problem. Now, formulate the model. Basically, here we have already formulated the model. So our model, the classical representation of our LP model would look like that. So first of all, I will copy the objective function. I just want to write it down as if you would do it if you are asked just on the exam to formulate the model. So this is my objective function. Then I write down here subject 2. Or instead of subject 2, I could write ST, which is short of subject 2. And here I enlist all my constraints. And constraints I have already here. Yes, it's quite lots of space. We don't need it. And one more, non-negativity constraints, of course, which I didn't copy. So this is the model, mathematical model without any non-necessary explanation. And by this, we have finished the bullet point A of this exercise. And we formulated the linear problem, a linear formulation for our problem description. It's the first step to find the answer. An answer we are looking for are, of course, production quantities of the both types of the paint. So after we formulated this model, so how can we use this model? And the next step, always the second step after we formulated the model in mathematical form, is to take this model, put it into the software, press the button, so to say, and then software will provide us the optimal solution. Optimal solution, this is the values of our decision variables that gives the best value of the objective function. So in our case these are x1 and x2. There are many kinds of software which could take mathematical model as an input and provide us some answer. For the first classes, we will use Excel solver to find the answers for the linear optimization model. The Excel solver is not the focus of this course, so it will not be asked on the exam, and we will use it now just to get some solution and know the main idea. To use the solver, first we create the empty file, Excel file. In this file, we will formulate the model and then solve it. And then we open this file. So here is this file. Then we formulate the model in the Excel worksheet. And for the solver to work, solver it's an add-on for Excel. First, you need to activate it. So to do that, you go to an Excel to file, to options, then to add-ins, and here you choose here Excel add-ins, you press go, and here you need to check the solver add-in and press OK. In my case, of course, it's already activated. And after you activated the solver add-in, in the data tab, you will see the solver button. We will check it a bit later. So now we will start from the model formulation. And on this Excel worksheet, I will enter all the input data and I will define the decision variables. So we start with the decision variables. So it will be decision variables. It's not important, so to say, which labels you provide here. I do it just for our understanding. And then what decision variables do we actually have? We have x1 and x2, and the meaning of them is the production quantities. So I write here production, let's call it just simply like that. We have two products, and therefore two decision variables. So this column C here, it will be related to paint 1, and column D to paint 2, which are external and internal paints. So first column will be external paint, second will be internal paint. And for these two products, we have production amounts, which are decision variables, and this is basically what we want to find, production amounts. So these are decision variables. As for now, I will put here values 1 and 1 to have some values there. All right, then here comes our data. So here go the parameters. Which parameters do we have? They all are present in our model, and they also are present in this table. So this is the usage of material 1 and material 2. Therefore, here will be material 1 requirements, and in the row 4 will be material 2 requirements. And these requirements are 6, 4, 1, 2. 6, 4, 1, 2. Next parameters that we have and that we will use, it's profit per ton and daily demand. Let's write down here profit per ton. This profit is 5,000 and 4,000. And demand is 4 and 2. 4 and 2. These are all parameters that we need, I guess. Do we have anything more? Yes. We also have the available amount of every material, but I will not include it now in the parameters. Now, next, what goes when we have the parameters, we write down the constraints. And first constraint is material. For material 1. Now, this constraint, it is here. It's basically the usage of material 1 should be less than available amount of this material. So the usage, to find the usage, we multiply the requirement of this material for the exterior paint, then for interior paint, and then find the sum of it. So let's do exactly this in Excel with the formula. To do that, first I write down the formula. What will be the usage of this material 1 for the first product for exterior paint? And it will be equal to a requirement of this material, which is in the cell C3, multiplied by production of the product of exterior paint. So with this formula, I can calculate the amount which will be used of material 1 for the production of exterior paint. Of course, if I change the amount of production line, if we decide that it will be 2, the usage of material, it will be 12, so it's double. Then if it's 3, it's 18, so it will, this is the dynamic formula which changes according to the parameter value, which is given, and production, which we calculate by ourselves. Same I do for the interior paint, the same formula, but with the requirements and production amount for interior paint. So it will be, in this case, if production is 1, it will be equal to 4. Now, this was the quantities for every product separately. Now we want to find their sum. I will also use dynamic formula to that. We'll use formula sum, but you can just use plus. So this will be the total amount of material 1, which we'll use for the production of both paints. And we know that according to this, to the constraint, so this left-hand side, which is the total amount used for of material 1, it should be less or equal than 30. So I can write it down here that it should be less or equal than 30. Yes. And now I do the same for the material 2. So I just multiply requirements of material 2 by the production amount and drag it. This is the same for material 2. I also want to find its sum. So 3 for this production amount, it will be the amount which we need of material 2 to satisfy this production quantities, and it should be less or equal than 6, because 6 is the parameter. It's our amount that we have. Now, next, the requirements or constraints that are this one. We just say that we cannot produce more than the demand. Okay, let's also formulate it. So we will say that first constraint is demand of exterior paint. And this demand, let's look at the constraint. It says that x1 less or equal than 4. So here we can imagine that there is a coefficient 1 here. Yes, so the left-hand side, it will look like 1 multiplied by x1, and x1 is production amount of paint, exterior paint. Yes. Then for this constraint, in the column for interior paint, we have nothing. So it's actually, we can imagine that coefficient is 0, but we don't need to write down here. To be consistent, I will put some value here, because we put always sums here. So the total of the right-hand side, I will copy it like this. So again, it's 1. And it should be less or equal than demand. And demand here we provided in the cell C6. Of course, if I would like to change demand, it's not a decision variable, but if someone would tell me, now according to our report, the demand will be 3, if I change it here, it will be updated in the constraint. Let's print it back. In the same way, I do the demand for interior paint for the second product. Again, this constraint in the left-hand side for exterior paint, it has nothing, but it has the coefficient 1, which is basically here, which we can imagine. We just don't write it. And it states that this production amount of interior paint should be less than demand of interior paint, which is 2. So again, I just write here. I don't need to write here 1, but to do it in the same way as we did for material constraints. Then I multiply it by production amount. Here again, it's not that required that I do it, but I always have in column E the sum of the left-hand side. So it's again 1 naturally. And it should be less or equal to demand, which is 2, if I'm not mistaken. Yes, this demand, it's 2. Now, we could also here provide the non-negativity constraint, but it's redundant because almost all the software that is used to solve the linear optimization problem, it assumes this non-negativity constraints by default. So if our decision variables cannot be less than 0, we don't need to mention it often in the software because it assumes to be like that. And only if we have some special case when decision variables can be negative, and they can be negative for some problems, not for production problems, but maybe for some problems where defined, for example, our costs. So we want to make a decision how many costs do we want to experience, and negative costs is something like income. So if we decide to have an income instead, it will be negative. If costs are positive, these are costs. So there are situations when decision variables can be really negative, but not the case here. So we have a default case. The next, what we need is the objective function. And for this problem, our objective function, this is basically our profit for this problem. And how do we calculate the profit? We did it already mathematically. It's here. So to calculate the profit, we multiply the production quantities with the profit per ton of the product. In Excel, it will look like as formula. So what will be the profit from exterior paint? The profit from exterior paint, it will be equal to the profit per ton, which we produce of this paint, multiplied by the production quantities of this product. The same will be for the interior paint. So we calculated in the same way, but for column D, which is related to interior paint. Now, here again, the same as we did with the constraint. In a column E, we calculate the total, and in the specific case, total will be our total profit. And we want to maximize this profit. As I say, maximize is not always the case. Sometimes we might need to minimize it if we work with cost, for example, or many other things. Now, and this is basically all the data that we have for this problem and all the objects of the model. We formulated them as hard-coded numbers if they are parameters, or some formulas because they depend on parameters and our decision variables. Now, to make it more clear, let's maybe draw some borders to see what is where. So first we have decision variables, then we have parameters, then we have constraints, and here is the objective function. I will make parameters bold because some of parameters I also wrote them here. So this right-hand side, which is the amount of material that we have and in demand, I also included there also parameters, and material requirements I didn't write down here because so how exactly you represent it, it's not so important. Now, an objective function. This is the model. Now, when we have this model in Excel formulated in this way, we need to explain solver what is what in this formulation, and then we will be able to get the answer. So let's now go to the data tab, press solver, and then we see the dialog box, which actually asks us, so where are the objects of the linear model on this worksheet? We need just to explain the software solver where they are. So in first it's objective. So it asks us where is the objective. An objective, it's in the cell, in our case E11. So this is what we want to maximize, and this is the total profit. We calculate it, but this is the cell where we have the total profit. We want to actually maximize it. We could choose here minimize or set some value to something, but we want to maximize it. Then here we are asked by changing variable cells. So this we need here to mention or specify the cells in which our decision variables are located. So I press this icon, and our decision variables are located in cells C2 and D2. So I press the left button and select this area. Then we can press enter. So we chose these decision variables. Then it's also important, you see here, it's ticked that make unconstrained variables non-negative. And that the things which I talked before, that we just say by it that all decision variables should be non-negative. Therefore, since we choose it here, we don't need to mention anywhere in the data in the worksheet that decision variables are non-negative. Next step, we are asked to specify the constraints. So subject to constraints. Again, it's similar as we did in mathematical model. We want to add constraint. And first constraint we add, it's the material one constraint, so cell reference. This is the sum of the left-hand side, and it's exactly here in E7. This is the total usage of material 1. Press enter. Then we choose here which sign do we want to have, and it should be less or equal, the same as in the mathematical model. And actually we mentioned it here on the worksheet. And then constraint, or the meaning of it is right-hand side. So total usage of material 1 should be less or equal to what? To 30. And 30 we have in the cell G7. Actually, we could even put here not cell, but the number 30. Yes, but since we want to have something like a formulation in the worksheet to have a visual understanding, and then we can dynamically modify the data in the worksheet without changing these hard-coded numbers, we just put here the reference to the cell. Now I can press OK, or I can press Add to add one more constraint. and I do the same for the material 2 requirement constraint. So E8 should be less or equal to G8. Then I add one more constraint, and you can imagine if we would have here not 4 constraints, but 20 of them. And in practical examples, you might have basically even millions of these constraints. It would be quite a long process, even in Excel, to add it. So there is one trick. When you provide the left-hand side, you can provide the left-hand side at once for multiple rows. So what does it mean? So when I choose the reference, I want to add next demand for exterior and demand for interior paint constraints. So I don't need to add them 2 times or in 2 steps. I just can select this left-hand side for both these constraints. Then I choose here the less or equal because it's the same for both of them. We don't have something like equality or more or equal. And then here at once I can choose the right-hand side for these both constraints. And then the solver, it will know that for every row, left-hand side should be less or equal than right-hand side. And if I would have many of these constraints, and if they have the same direction, or less or equal or more or equal, I could do it at once. So I added all my constraints, pressed OK. Here we'll talk about it a little bit later, which method do we use. This problem, it's linear problem. About this we will also talk why it's linear and not something like nonlinear or quadratic and so on. But here as the method we will choose simplex LP. We don't, in this course, we don't really look at the solution methods. So we don't look how exactly software provides you the answer. Our task is to formulate the model correctly, as we did here, then provide it in a right form to the software, and then we press the button and get the answer. This is our task. And it's quite a realistic task because how exactly it works, it's more science than practical task. So we formulated all the necessary objects for this linear model. We don't need to look at the options. And then we can press solve. So then we have a dialog box with the answer, and it says that solver found a solution. There can be exceptions. Solution sometimes isn't found because it's not possible or because there is no solution. We'll look at it also later. And here we choose keep solver solution. It means that now the values of decision variable cells were updated to the most optimal solution. So it's 4 and 1. And I press OK. And now here I have the data, and at the same time I have the solution. So according to the solver, the best or optimal solution for this problem, which maximizes the profit, is to produce 4 tons daily of exterior paint and 1 ton of interior paint. Of course, our parameters, they didn't change, but when I look at the constraints, since here were the dynamic formulas, I can see that according to these decision variables, I will use 28 tons of material 1 out of 30 tons available. I will use all available amount of material 2. You see, we don't have any free amount. Then I will satisfy, so to say, all the demand. So even from here, I could, if I need to make some more business analysis, I could see that what is a real stopper for increasing my profit even more, it is the demand and material 2, right? And material 1, it's not limited because I have some spare material, even spare material with the optimal solution. Now, when I go to the objective function, I see that from exterior paint, I will get a profit of 20,000, and from interior paint, I will get a profit of 4,000. And my total profit or value of the objective function, its optimal value, it's 24,000. This is the maximal profit which I can get given this business situation and these parameters. And as you might guess, this was the answer for bullet point B. So find the optimal solution, and we found it in Excel solver, and the optimal solution is 4 and 1. I will note here optimal solution, it's 4, 1, and so it will be production exterior paint, prod interior paint, and then let's write here down also the profit which we get with this solution. It's 24,000. This is the best profit that we can get. Now, next question is C. What are several examples of feasible and infeasible solutions? So, what are basically feasible solutions? Feasible solutions, by definition, this is any solution. So it's any combination of values for decision variables for the production that satisfy all the constraints. So that do not violate any of the constraints. For example, so we had this is optimal solution for 1. If I change this 4 to 3, I see that when I look at the constraints, none of the constraints are violated. So our amounts of materials which we use for every material, they don't violate the constraints of amounts which we have for these materials, and the demand, it's still lower, so our production is lower than demand. Same if I put here interior paint 0, if we decide don't produce at all of this interior paint, again, none of the constraints will be violated. But one thing that I see that when I change my solution from the optimal one, my profit that I get, it's lower than the one which I have with the optimal solution. Feasible solution is the kind of solution when we don't violate any of the constraints, but value of the objective function, it might be lower than that when we apply the optimal solution. So let's write down here feasible solution 1. When we produce exterior point 3 and interior paint 0, and we get then 15,000. Or feasible solution 2. It can be even, let's say, 2 and 1. And we get then profit 14,000. Of course, profit of the optimal solution is better. But it's also important to mention that optimal solution is also a feasible solution, because optimal solution is the solution which doesn't violate any of the constraints, which is feasible solution, and also it gives us the best possible under these constraints value of the objective function. There are some cases when we have several optimal solutions. So for some problems, it might be the situations, and we have here, for example, 4 and 0, sorry, or 5 and 2, and both of these solutions, they will be feasible, and they will, due to some reason, provide the same profit. It depends on the parameters and numbers. Then we would say that we have several optimal solutions. Now, another question is, part of the question is, so find several feasible solutions, and what are infeasible solutions? An infeasible solution, it's so antonym to the feasible solutions, it's opposite. It's the solution which violates some of the constraints. So the first infeasible solution, for example, solution -1, 1, which basically doesn't make so much sense. And as I said, we didn't mention here in this formulation on the worksheet the non-negativity constraints, but we know that we cannot produce a negative amount. So this solution violates this non-negativity constraints, and therefore it's infeasible solution. I will not write which profit we get, because profit for infeasible solutions, for us, it's not that interesting because this is kind of solution which we cannot even take into the consideration. Another infeasible solution, which would be it's 5, 1. So you see, according to this solution, the profit is 29,000. So it's almost like, it's exactly 5,000 better than the profit of our optimal solution. But we cannot use this solution as optimal because it's violate constraints. Which constraints does it violate? So it violates 3 of 4 constraints. Then we use more material 1 that we are allowed. We use more material 2 than we are allowed. And we produce 1 ton more of the exterior paint than the amount of exterior paint we can sell. Yeah, therefore, this solution is also infeasible. So if solution violates at least one of the constraints that we see here on non-negativity constraint, then this solution is infeasible. So infeasible solution 2 will be 5, 1. You can imagine we can find an infinite number of infeasible solutions. It's C1, 5, 2, and so on. Now, there are some situations when we don't have optimal solution, and it normally happens when we don't have, or it only happens when we don't have any feasible solutions. So we might have a problem for which whatever, in this case, pairs of the decision variables, values for decision variables we take, we always get the infeasible solution. And since all the infeasible solutions are not acceptable as feasible or optimal solution, we don't have solution for the problem and we don't have optimal solution. Let's try something here. So let's just imagine that instead of this data which I have, I got the information that for material 1, I have the available amount of it, only 3. So instead of 30 tons per day, I have 3 tons per day. In addition to that, our investors of the company, they say that the company can only exist when our profit is, let's say, at least 10,000 euro dollars. What was it? Yes. So if we cannot guarantee a profit of 10,000, it's not the feasible solution. Our company will just will not exist anymore. So we can add this requirement as a constraint, because constraints are basically requirements. So I will add it here. And so it says that our profit, something what will be now on the left-hand side, should be more or equal to 10,000. At least it should be 10,000. Now, this constraint will be profit requirement, new constraint. And how do we calculate the profit that we generate? Basically, we did it in the objective function. So for that, we multiply for every product the profit per ton of this product with the production amount. We did it for exterior paint, we do it for interior paint, then we find the total profit, which is the sum, and this sum, it should be more than 10,000. Now we see that for the optimal solution, which we had before, of course we satisfy, we don't violate the profit requirement constraint, but we would violate this new constraint that I updated. Now, let's do them. So this and this, it's something what I have updated. Now let's try to find the optimal solution using the solver for this problem. To do that, I again open the solver. I don't, oh, it's something broke here, it shouldn't. So normally I don't need to, but here it has some problems, so I need to update the material 1 requirement. It should be less or equal to 3. And then I need to add this profit requirement, new constraint, which is said that total profit should be more or equal, it's more or equal constraint, not less or equal, to the 10,000, which is the lower bound provided from our investors. we have an updated problem, everything else set objective. It's 12, decision variables C and D2. Everything else looks correct. So let's now try to find the solution. I press the solve button. And the solver says that solver couldn't find a feasible solution. It said that for this problem there are no any solution which satisfies all the constraints, and of course there are no therefore no optimal solution. I will press OK, and now look let's look more precisely. What do we have here? We see that it already put it automatically that to satisfy material 1 constraint, new updated constraint, I can produce at most like this amount of paint. So 0 and 0.75 tons. But with such a small production, which is limited by this material 1 constraint, I cannot satisfy this profit requirements, which was set by the investors. So from a mathematical point of view, for this problem, which we have now with this additional constraint and modified right-hand side, we have no any feasible solutions and therefore no optimal solutions. And from the business perspective, we would say that we cannot, under these conditions, satisfy the requirements of the investors. So this was the last bullet point of the first exercise. And in this first exercise, what we did, we just read the textual description. We defined all of the elements of the linear optimization problem or model, and they are the same with any kind of model. Big one, small one, practical one will be always the same. We formulated this model mathematically. Then we transformed this model into the Excel format, Excel solver format. We found out the optimal solution for that model, which we had, and we found out some feasible solutions which satisfy all the constraints but aren't always optimal. We found some infeasible solutions, and we even developed the model, or we modified this model that we have in a way that it doesn't have any feasible solution, so we call this model as infeasible. So the exercise number 2, basically, this exercise is also based on the paint production, the same company, the same setting. We will only add several, let's say, business specialities and try to model the situations which emerge from the business cases. And in the bullet point A, you have some more textual description. So it said that because of some technological reasons, to produce the exterior paint, which is this red column paint, product 1, the company just to produce at least start producing any amount of this paint, company should set up the production line. So you can imagine that to start producing this paint, maybe they should modify something in their factory, they should find a new specialist. So if they just start producing this exterior paint, decide to produce exterior paint, the company will experience the cost of 15,000 euro. Even if they decide to produce only 1 ton of the paint, still they will experience this cost. And therefore, it's like a small tip for the modeling. So the company now should not only decide how much of every paint to produce, 1 ton, 2 tons, 1.5 tons, but also whether or not to open the production line for this first paint. And we are asked to modify the model. And specifically, again, some tip that we need to modify the objective function and the constraints of the mathematical model for it to represent this decision-making process. So, according to the new process, we make, in addition, decision about whether to open or not the production line of exterior paint, whether it's worth it. So let's go back to the model. This was the model formulation for the initial version of this problem. And now we need to make this one additional decision, whether to open the production line of exterior paint, so for X1. So as I said, we need to make one more decision in this new updated problem. And this decision is whether to open the production line. For that, I will write all the updates in red, so we see the difference, or now better in green then. So, and here, to the decision variables that we had before, x1 and x2, we have one more decision variable, which I will call somehow differently, like, let's call it y. And the meaning of this decision variable is whether to start or not the production of exterior paint. So I will denote it in this way. So mathematically, this variable, it can get two values. It might be 1 if we open a line for exterior paint, or it's 0. So otherwise if we don't open it, right? So only two values it can have. It cannot have like 2 or 1.5. If we are not sure to open or not, it cannot be 1.5. It's only 1 or 0. And if we, according to the description, if we open the line for exterior paint, we will get the expenses of 15,000. So how can we model this situation? Again, we have now a new decision variable. To model it, we go back to the model. And so these first two values, they were profit or income that we get from every paint, but now we want to model the expenses. The expenses, they will lower our profit, so they will have the sign minus. Then our expenses, it's mentioned in the parameters, they're 15,000 if we open the production line. So how can we explain to this model that 15,000 should only happen when if open the line for exterior paint and minus 0 expenses, so we will not have any kind of expenses if we don't open that line for exterior paint. How can we do it? Because we want to have one model, but somehow it should have, according to our decision, different objective functions. You can think about it for a second. And after you thought about it, so to model this situation, of course, I will delete or delete this text. I just write down minus 15, which will be a coefficient multiplied by this new decision variable y. And now you can see that if we decide not to open this this production line for exterior paint, this decision variable y, it will have value 0, right? Because we set it here, yes, in our explanation to the decision variables. So it will have value 0. And therefore, we'll have an objective function minus 15,000 multiplied by 0. And of course, whatever we multiply by 0, it will be always 0. So this all will translate to 0 in this case. So it will be 0, exactly what we want. On the other hand, if we will decide to open this line, y will have the value 1. And when, in this case, coefficient minus 15 is multiplied by 1, so it doesn't transform into 0, and it keeps its value 15. So in this case, this all will be exactly minus 15. So that's the amount of additional expenses which the company will experience, and this will lower the profit, and of course the maximum profit. So this is the modification to objective function. Of course, now we also need to add the some explanation in the mathematical model about this decision variable y. And actually, we mentioned here that this decision variable is slightly different from the x1 and x2 because it can have only two values, 1 and 0. And such kind of decision variables, They are called binary variables. It's like binary code in which every value can be only 0 and 1. So this decision variable is also a binary variable, and we need somehow to specify in our model that this variable is binary. And for that, we will add one more constraint, because this is the constraint. It limits the values which this variable can get. And we can explain that it's binary in several different ways. We can simply write down that it's binary, or B. It will be completely valid mathematical notation. But we can also say that this variable, it can take values only from some specific set. And here we will enumerate the values which this variable can get. And this is 1 and 0, or 0 and 1. So it also says that it's binary variable. I will write down here now explanation. This is binary variable. And such variables as x1 and x2, which can have, even so they can have only positive values, but we could also produce like 1.5 tons of paint, or 1,25 tons of 1.25 tons of paint. They are called continuous variables. Continuous variables. And then also we might have some variable which can have only integer values, for example. This is the third type of decision variables. So let's say that we might have some decision variable z, which could maybe take all positive values, but all positive values which are only integers. So 0, 1, 2, and so on to infinity. All right. And this kind of decision variables we would call integer decision variables. You can see that binary decision variables, they are the subclass of integer decision variables, right? Because 1 and 0, this is also integer values, but they are limited by only 2 values. And for integer variables, it can be any integer value. And the example of integer decision variable, they could be, for example, if you would make a decision not about the production of paint, but about the production of cell phones. So it's natural that you cannot decide to produce 1.5 cell phones. Even so, you can produce 1.5 tons of paint, but to produce 1.5 cell phones makes no sense. Or like 100.3 cell phones. Or if we would talk about people, like if our decision would be related to how many people we want to order job for in some company. So also you cannot offer job to 1.5 people. Persons. Yes, it makes no sense. So in this case, our decision variable would be integer. In this example, we talk about binary variable. This is one additional binary variable. So we modified here the objective function. And in the tip about the assignment, we are also asked to modify the constraints. So, and why do we need to modify these constraints? Why isn't it satisfactory what we have now in the model? Let's think about it a little bit. So when I will try to, or solver, or even if we would do it manually, if we would try to find the maximum values for these decision variables, of course, we would always be motivated to set this y to 0. Because if it's not 0, it's 1. And if it's 1, we have smaller profit. Yes? So we like always want to set it to 0. Yes? And then let's imagine that we set it to 0, so we don't have this. And then when we look at these constraints, there is nothing in the constraints which says, all right, if y is 0, you cannot produce x1. Because this is the case in the description. To produce at least some exterior paint, x1, we must open the line and we must experience this cost. But according to this formulation, we are motivated not to open this line, but in the constraints, there is nothing what constrains us and says, All right, if you decided not to open the line, if y is 0, you cannot produce this paint. And we want somehow to add the constraint which links y and x1, and which said that without production line, production of the x1 is not possible. Since we want to link these two decision variables in the constraint, in one constraint, probably in this constraint, these two decision variables will be present, what is natural. So let's think about what kind of constraint will really control or describe this relation. So this will be the constraint where x1 and y are present, both. And then maybe some coefficient. And then we need some kind of relation, equal, less or equal, more or equal. So if I would put now here, for example, equal, well, does it make any sense? So I see that if y is 0, then it will force, according to the equality, x1 to be also 0. So this is nice. That's what I need. But let's look at another situation. If y1 will be 1, so if I decide to produce, to start the production line, again, I will experience the cost. But according to this constraint, this equality, in this case, I will be forced to set x1 to only 1 ton, right? Because they should be equal. But that's not what I want to express, because according to the description, if I open the line, I can produce any amount of exterior paint that I want, not only 1 ton. So it means that equal sign is not suitable for us. You can stop the video and maybe think, maybe somehow recombine them, don't put them, these decision variables in left-hand side and right-hand side. You can try some brainstorm. Now let's try. So I didn't like that y, when it has value 1, it really limits my production. So let's try another sign. So if I will put here the less or equal, again, the same logic, if y will be 0, it will force to x1 to be 0. That's what I want. Yes, because x1 should be smaller than y. But if y will be 1, I will again force x1 to be not 1, but to be something between 0 and 1. Because I have here constraints that x1 should be bigger than 0, and this constraint, when if y will be 1, it will force x1 to be smaller than 1, which is also not what I want to have, because I don't want to limit x1. And the same analysis you can do with if you switch the sign, so whether it will work for you or not. So if you will say that x1, it's always then bigger or equal to y, and of course it will not work, because then the value of y equal to 0 will not limit the x1 1. So the approach here, which is often used, is to use the artificial, let's say, coefficient near y, and we will use m for that. This is m, it's so-called m notation, or m value. This m, it's some very, very huge number. So this is kind of a production of exterior paint, which we will not even think about it. So millions of tons. So let's write down that m is big number. And how this then constraint works? So let's again test values. So if we have y equal to 0, m multiplied by 0, it will be 0. And then if we don't open the line, we don't want to, we are not allowed to produce. And you see that if right-hand side will be 0, it will say that x1 should be smaller or equal to 0, so it will be also forced to be 0. That's what we wanted, and we already got it before when we didn't have big M. But then let's see if y is 1. So if y is 1, so m is multiplied by 1, and m is some very, very huge number, and our x, it should be smaller than some very huge number multiplied by 1. So x will be able to take any possible values in it needs. So it will be like this, and then it will say just that x1 is smaller than some very huge number, and in other words, it will not limit xy1 whatsoever. And then the properties that we actually need, because here in the first red line here, we say that if we don't open the production line, we can produce x1, and if we open it, the second line says we can produce any amount of exterior paint, because then x is limited by m, which is almost like infinity. So that's exactly how we model this situation. So we add the constraint, which looks like this, with big M, where M is big number. And this is the modified model to satisfy the descriptions that we have here. And we are asked to find a solution for this modified problem in Excel solver. I will not, again, reformulate this model. We can just look at the solutions which are provided to you in Moodle and see how it's modeled there. Because the main idea of this exercise for you is to understand the modeling and not to its implementation in Excel. So this is the formulation, modified formulation. We have another column related to decision variables, which is related to decision variable y. We see that we also modified the objective function. We added there one more element, which has negative, which is negative because these are costs, and then we multiply the coefficient of fixed costs, so it's input data, input parameter, which are 15,000, and we multiply it with the value of y. Y can be 0 or 1. Another modification that is here, it's the one more constraint, which is big M constraint, and this represent this mathematical inequality. So again, we see that we have in the left-hand side, it's simply x1, so production amount, and in the right-hand side, it's the multiplication of big M, and here we took big M is nothing close to infinity, but it's 100 because it's sufficient in this case. Yes, but if we would talk about some very huge production amounts, 100 maybe wouldn't be big enough number. And then we multiply by the value of decision variable y. Yes. Now when we formulated it, we go again to the solver. We have here the dialog box. So again, we set the objective to be the profit, and profit, it's the profit from every product minus the costs which we might experience. Then constraints are, so I will delete it. Set objective. Yes, so the constraints, I will delete this constraint and reassign it so you know. In the constraints, as we did in the mathematical model, we add this constraint. We just said that y can be two values, 1 or 0. So we do the same in here in the solver interface. We add constraint. We say that this cell or this decision variable E2, it should be binary. So instead of some inequality sign here, we just choose here bin, which means binary. You can see we could choose here int, which means integer, but we choose binary. and I press OK. And then here we have the constraint for, it's like one constraint for all the constraints that we have. I showed this tip before. So we just say that left-hand side for every constraint should be smaller than right-hand side. All right, and we don't need to modify anything more in this problem. Now, when we press solve, we will find the optimal solution, but optimal solution was actually here before. So we found the optimal solution. And actually it says, if you will check this optimal solution production quantities for the exterior and interior paint, we see that it didn't change from what we had in the previous variant of the problem. So it basically says that, all right, even if you experience additional costs because of opening production line for exterior paint, still do it because it's worth it. And we can experiment a little bit with it. So first of all, if I would put that y is equal to 0, we would see several things. First of all, of course, costs, they disappear. We wouldn't experience any costs, and our profit would be much higher. But we can see that this solution, it's not feasible. It's infeasible. Why the solution is infeasible? Let's check our constraints, and we see that 4, it's not smaller or equal to 0. So 0 is smaller than 4, of course, so we would violate this big M constraint. And this big M constraint is exactly that constraint which was specifying that if you have no production line, you cannot produce any of exterior paint. Then we can also play with parameters. Let's imagine that we would experience fixed costs if we open the production line of not 15,000, but let's take some 100,000. So if it's very expensive to open the production line, let's check now whether it would be worth to produce exterior paint in this case. Maybe we would just focus on the interior paint. So I go to the data solver, and I don't need to modify here anything because I didn't add any more components. I just modified the value of the parameter. And I press solve. So solver again found, of course, the solution, but we see when the fixed cost for the exterior paint production line increased, our solution says, all right, in this situation, it's not worth at all to produce the exterior paint, because what we see from this analysis, obviously, starting this production line is too expensive, and the only focus on the exterior paint, and then it says produce only 2 tons of exterior paint. Why does it happen like that? Yes, we can see from the constraints that demand, that the limiting factor here, the constraining constraint, let's say like this, it's 2. It's the demand which is 2. And also, so such constraints which really limit something because others don't limit, they are called efficient constraints, and these constraints, we might call them non-efficient or not effective because they don't really influence our solution in this case. And this was bullet point A. So here we looked at the integer optimization, right? So linear optimization, it's the case when all our variables are continuous. And if some or all of the variables, or let's say if all of the decision variables are integer of binaries, then we call it integer optimization or binary optimization. And if, as in this case, some of the decision variables are continuous and some are integer, we call it mixed integer optimization and mixed integer problem. Why it's so important whether we have integer, binary, and or continuous variables? Because then slightly different solution methods are used by the software. And when we have a big problems, solution of integer or binary problems or mixed integer binary problems, it's often to find the solution for such problem, it's more difficult for the software. It takes much more time and sometimes can be even not solvable in a modern, like in the short time, in a moderate time. Next question which we are asked, it's again about the notation. So it said that use some notation to formulate the general model. So it says only letters, no numbers. And how can the model be generalized for any number of products? So so here we have something which is called sum notation, then general model, so only letters, and how would model change if we change amount of some elements. So let's first look at one thing, and the thing is that here, even in Excel, so on the worksheet, we have our data for the model. Then this model is already in the Excel solver, right? And if we don't add any kind of products, if we don't add new amount of constraints and new constraints, if we only want to modify the coefficients which are already here, like when I did with the fixed costs, we don't need to reformulate this model. We only change this coefficient, like again to 15,000. We again go to our formulation in solver, and we don't need to modify here anything because we only change the parameter. We didn't make any structural changes to the model, and we can again resolve it without modifying anything like that. So this universality is quite important because if you would have let's say you would want to experiment with different parameters, it wouldn't be so convenient to reformulate this model again and again, and just to look what happens if we change some value of some parameter, or like if our demand will increase, if we want to check what will be the production amounts and profit and production amount, it will be not so convenient to always change the model, and this specific formulation allows us to do it. If we go to the mathematical formulation again here, if we would change some parameter values like the requirements of material 1 to produce exterior paint, we wouldn't need to modify a lot in this model. We would just change this coefficient, let's say, to 3. And that's it. So the same situation here. But what happens if we would have another business case where everything is exactly the same, but we have one more additional product? So we have exterior paint, interior paint, and then we have here one more product, X3, which is like oil for wood, some other similar product. And then in this case, when we have this mathematical formulation, we would, of course, need to modify the objective function. We would have to add here actually it would be not x1, but x3. Sorry. We would need to add here coefficient, which is profit of x3 and multiplied by x3. Then we would have to modify the constraints, because again, we would add here everywhere some coefficient for x3. We would need to add here yes, x3 is bigger than 0. So we would really need to rewrite this model, and the same would happen in Excel. We'd need to add here one more column for the third product, and so on. Or what would happen if we would have one more material? So if situation changes and we would need not only 2 materials for the production of exterior and interior paint, but we would decide to improve the recipe of the paint and add one more material. We would need again to add here something from material 4, and it would be also the similar constraint with similar idea, but with another coefficients, with coefficients only for material 3, less or equal to some requirement. So again, we would have to rewrite this model, but these changes, they are not some very big strategical structural changes. It's only changing the recipe of the paint, or if we add one more material. Therefore, to have some higher level of abstraction and not to rewrite this model again and again if only small changes are happening, we have more convenient notation for that, which is called we will call it in this course as the sum notation. We will use some notation for this model formulation, not to make things more complicated, without fixed costs. So for the initial version of this model, right? And let's start from the objective function. So our objective function, if we would have three products, it would like max, then 5,000 x1 plus, what is it, 4,000 x2 plus some other profit per product x3. If we would have even more products, it would be some other coefficient x4 and so on. We could continue to any amount of product that we decide to produce and not produce. And you see that not so many things are changing in the objective function. So first simplification that we can do, we can say that instead of using some specific numbers in the objective function, we will use the coefficients or letters for that. So we'll say that C I is the profit per ton of product I. And then we know that exterior paint, it's product 1, interior paint is product 2, some another product it would be product 3, one more product would be product 4, and so on. Yes, and we know that C1 it's 5,000, C2 it's 4,000, C3 it's, let's say, 7,000, and so on. But for our so to say abstract formulation, it's not so important. So now let's write this objective function and put the C coefficient instead of the exact numbers. It will be C1 multiplied by x1 plus C2 multiplied by x2 plus C3 multiplied by x3 plus, and so on, plus Cn multiplied by xn. What is n? I will again write down. This is the number of products. So in the initial formulation of this model, we had exterior paint and interior paint. So the n was equal to 2 because we had 2 products. But if we would have 3 products, not so much changes. Yes, if n is equal to 3, we would continue this row until n is equal to 3. If 4, it's 4. If it's 10 million, it would be 10 million product, but it doesn't change a lot. And now, how can we even shorten it even more? Of course, for that, we can use some notation. You never tried it. Just you can Google it how to really do it. But so how do we shorten it further? We use that it's sum of C I multiplied by xi. So, and what are these values of I? So I starts from 1. So for the first element, I will be 1, and it ends by n, by the number of products. So n, right? So if we this sum, it can be easily transformed to this second form of objective function, which I here presented. So for, let's say, 2 products, we will have 2 elements here. For 3 products, n will be 3, and we will have 3 elements in this row. And for n elements, this sum notation is equivalent to this notation. So this is the formulation of the objective function using some notation without using any letters or numbers, because we know that in the textual description we are provided what are the costs for every product I and how many products do we have. This is the objective function. Now let's look at the constraints. We will start as here from the demand constraints. So demand constraint for the first product, it looks as x1 more than 4. For the second product, looks x2 smaller than, sorry, not more than, I guess, 2. If we would have 3 products, it would be x3 smaller than some value, some demand of that product. x4 would be again smaller than some demand of this product, and we would do it until xn, so until the number of the product smaller than again some demand of the product. Now instead of these numbers, let's say that di, see before it was ci, now it's di, it is the demand of product I. So before we had letter C, it was profit per ton of product I. Now we again substitute exact numbers with the letter di, some level of abstraction, it's demand of product I. And then these all constraints, they will look like x1, it's smaller than d1, x2 is smaller than d2, and so on until xn is smaller than dn. So from here, we see that, so first of all, we don't need to use here any kind of sum notation, but on other thing which we see is that this constraint that some xi is smaller than di will be the same constraint for every product. So for product 1, it will be x1 smaller than d1. For product 2, it will be x2 smaller than d2, but it will be always x1 smaller than d1 for all the products. So we can rewrite it as xi is smaller than di for all the products. So we can even write it down that for all I equals from product 1 until n, until the last product. So all products have the same constraint. And it's important that here I don't use any kind of sum notation. I just say that this constraint xy smaller than di for all products. And another more way how we can formulate it is again x1 x I smaller than di, and then instead of writing for all, I just write this sign, which is so to say a rotated 180 degrees for all I, and again from 1 to number of products. This is the equivalent version of this formulation. Now I don't need to restate here that n is the number of products because I wrote it before. But of course, when I provide such an abstract formulation, I need to specify what is n. And di, as it's specified here, is the demand of product I. So this were the demand constraints. Let's look at not at the material constraint, but at the non-negativity constraints. We can also write them down in exactly the same form. So we can write down that x1 is more or equal, and here we don't need any letter because this non-negativity is always 0 for all the products. So we cannot produce less than 0 products. So it's x1 more than 0 for all products from 1 to n for all the products. These are non-negativity constraints, which are only one line, but if you rewrite it down in more explicit form, it will be n lines of constraints. And now we look at the material constraints. And material constraints, this is, so to say, this is the most normal constraints that we always meet. It's very rare. Rare, it's not the precise term, but sometimes such constraints as demand constraints or non-negativity constraints, sometimes they are not even called the constraints, sometimes they are called upper and lower bounds. When you have on the left-hand side only one element or one decision variable with coefficient 1, and then such bound constraint or this bound, it says what maximum or minimal value this decision variable can get. So sometimes this and these constraints, they are called bounds. And this material constraints in our example, this is the most, so to say, classical linear optimization constraints. So let's look at them more precisely. I don't want somehow to rewrite them. I will just copy them. Yes, these are they. Now, we don't need this non-negativity constraint. But yeah, I will write them a bit more clearly. So these are constraints for the material 1 and material 2, and for product 1, and of course product 2. So what would happen if we would have more materials? Then we would add one more row, one more constraint, one more row. So it would be some other constraint with x1 and some coefficient, which is the requirement of that material 3 for x1, and then another coefficient for the material 2. And then this sum would be smaller, equal to some available amount of that material. Of course, we would have material 4, again, would add another row and another row, so it wouldn't change dramatically. Now, what would happen with this constraint, with this, in our case now, 3 constraint, if we would have one more product? If we would have one more product, we would need to add here one more, so to say, imaginary column for product 3. So I would move all these guys and actually I will do it, all new things I will do red. So this is red. And then if I add one more product, of course I will add plus for the material 1, then the requirements of material 1 for this product, which will have index 3, x3. And then, of course, this left-hand side, which will include 3 coefficients and 3 variables, will be still smaller than requirements of material 1. The same will be here, again, some coefficient, requirements of material 2, and all the sum is smaller than 6, and in the last row, exactly the same. If I would have the same as with materials, if I would have the one again more product, again, in the same way, I would add one more column. So let's now substitute the 3 dots and these exact numbers with some letters, as we did before. So we could use any letters here. Let's say that requirement of material J to produce product I, we will denote it with the letter R. Requirements R. So R, J, I. J, I's index. Now it consists of 2 elements, because we need, so to say, to connect 2 entities in our model. This is the requirement. These are the requirements, or is the requirement of material J to produce 1 ton of product I. Now, what is this 6? This is the requirements of material 1 to produce product exterior point, which we decided that it's product 1. So I can write down here that it is R11. Now, what is 4? 4 is the same thing as R11, but for product 2. So it's again the requirement of material 1, so R1, but now for product 2. So we change the second index to 2. And as you guess, for the third product, we almost automatically change the second index to 3. If we would have here product 4, for it, the index of material 1 would be R14. For product million, the second index would change to million, and so on. And also we can observe that in this first constraint, in material constraint, which is related to material 1, all first index for all the requirement coefficients will be always 1. And it corresponds to the material and to the row number of material constraints. Now let's go in the same way to the second row. And this 1, it's again R, but it's now for material 2. So it's requirement of material 2. So it's 2 for product 1. Then 2, it's R2, 2. So material 2, product 2. And here R2, 3. You can try to do the third row, but obviously it is R31, R32, and R33. One another thing that we can observe, we already saw that for the rows first coefficient is the same, but for the columns which are related to the product, the second coefficient is the same. So we see that in the first column, second coefficient is 1, in the second it's 2, and in the third it's 3. Now we got rid of these numbers in the left hand side. Now let's manage something with the right hand side, because there we also have the numbers which are the available amount of every material, material 1, material 2, material 3. And to substitute them, I will use some letter which will be B, J, right? We don't need here 2 indexes because this is the available amount. This will be available amount for material, and it has nothing to do with product or any other entity in our problem. So it will be the available amount of material J. And again, let's go to the constraint. So 30, it's B1 for first material, then 6, it's B2, and as the last imaginary right-hand side coefficient, we don't have exact number, it will be B3. Now we see that we already have quite a large amount of abstraction, so we substitute all our numbers in the constraints with letters, which are here. But now we see here that we have lots of pluses, so it looks something like a sum. In left-hand side, we always have sum for the first material, then for the second material, then for the third material. So maybe we can also somehow shorten it, and let's concentrate on the material of the constraint for material 1. So in the right-hand side, I don't have so much to modified, smaller than b1. But what is here in the left-hand side? I see in the left-hand side, first index of R is always 1. And the second index is the index of the product, and it changes from 1, as well as for the coefficient, but also for the decision variable, x1, x2, and so on, from the first product to the last product, which our case is 3, but which we defined as n, the number of products. And if we now look at the how we define the objective function as sum notation, we had also there something quite similar when we had many coefficients and decision variables, and then we shortened them using the sum notation. Right? So we will do here almost the same thing. We say that the sum in the left-hand side of R, since now we talk about material 1, it's R always has index 1, but then I, because I is changing in this row from 1 to 3, multiplied by x, again with I. So every this multiplication element, it has the same index related to product. So x1i, xi, and then we specify here how this I is changing. And if we look here, this I is changing from 1 to 3, or from 1 to n. In the same way as we did in the objective function, we say that I is changing from 0 to n. And since here we talk about material 1 again, R has first index 1, and B has also index 1. Then you can do the same for material 2 and 3. It will be exactly the same thing. But R first index will be 2, second will be I multiplied by xi again, more than B2. And for the third material, it will be here n from I to 0, R 3 I x I more than B3. So this is the more compact form, and we see that it's already in the sum notation. But again, we can do here the same trick as we did with demand constraints and with non-negativity constraints. In the demand constraints, we have lots of the same constraints for every product. Now, if we would have many materials, not 3 but million of them, we would have exactly almost the same constraint, and only what would change is this first index of R and index of B. So we can again rewrite it in more compact way, and we can say that our material requirement or material constraint, it looks as the sum of R then J. Instead of exact number, we use J I multiplied by xi less or equal than bj. Then in the sum, so it's I. In the sum, I is changing the same as it was mentioned in this constraint from 0 to n. And this constraint is the same for every j in from 1 to the number of materials. Before we talked about products, now it's the same for every material. So until, let's say, that m, and we would need to mention somewhere that m, it is the number of materials or resources. Let's write down materials. So, and this is the most compact form in sum notation for the material requirements constraints. All right, I wrote here a lot, so now it would be nice to look at the final formulation of the model. And So this formulation, it's quite short. I would write it down again. So our objective is maximize, or I can copy it. It's maximize the profit we want to maximize the profit subject to, and then here we need to list all the constraints. First, I will start with the material requirements constraint. Yes, of course, we don't want to forget about M. And then demand constraint, which is x1 more x I is more equal to di for every product I in 1 to n. And then we say that xi is more than 0, again for every I. And this is now our model formulation. To have it, of course, complete, here we would write also where, and then we would explain all these letters in the way as I explained them here. So we would write down where M is the number of materials, N is the number of products, RJI, BG is this and that. So we'll just copy this textual description. But this is this model in the sum notation. And you can see that here, according to this abstract form, we don't really care about the number of materials or the number of products, because not so many things will change dramatically. And maybe when we talk about this model, we don't want to concentrate on details. We just want to first get some abstract formulation of the model. And this was the exercise 2, which is just extension of the initial problem. And here we looked at the two important points. It's the integer optimization or modeling, where we had decisions represented not by continuous variables, but represented by binary variable, which basically yes or no. I also mentioned it might be integer solutions or integer decision variables. And also then we looked at the more abstract but more universal notation, which we will call sum notation. And we used for that basically sum notation, and we used letters and no numbers. And we see that according to that notation, if we have 3, 4, 5 of any number of products, materials, and other components, we don't even need to rewrite the model. And now we go to the last exercise, it's more even the something slightly funny. So here it's called potato paradox, and it treats about the some interesting phenomenon in economics or in marketing, which was found by Sir Robert Giffen in 19th century, and he demonstrated that increasing prices on some product can even increase the demand for this product, which is slightly counterintuitive. This exercise it's the exercise for the linear optimization, so we will not discuss whether it really demonstrates this effect, and maybe there is some tricks in this textual formulation. But again, we have the textual description, and we will now identify all the elements of the model, because we will create a model for this problem. Yes. So we will now identify the decision variables, parameters, objective function, and constraints for this problem. So the data is that the food menu, Irish food menu, I guess in 19th century, it was consisting of two products, of potato and meat, and each of these products has some nutrition points. So the 1 kilo of potato has 2 nutrition points, and 1 kilo of meat has 5 nutrition points, whatever nutrition points mean. And that every person needs at least 20 nutrition points, so it's something like calories per day to survive. Then we are given the price of this product, 1 and 5, and the daily budget, so which is 15 pounds per day. And also it's quite important, it's mentioned here that every person, they have budget and they want to spend it mostly on the meat. So they prefer meat more. If they have opportunity, they would only eat meat. And then we somehow need to formulate here the optimization model. And we need to show what will happen if price changes. And here is the tip that to demonstrate the given paradox, we will assume the increase of potato price of 25%. So now the potato price is £1 and it will be 125 pounds. So we are asked them to solve it in Excel. Let's start from the linear model. So, and we start from the decision variables. So our decision variables from the description we see, so we want to consume as much meat as possible, right? So that's what we, as the citizens at the time, decide. We decide how much meat we consume, but for survival, and to survive we need 20 nutrition points, maybe we will have also to consume a potato. Of course, we don't want to consume potato, so we would like to keep it 0. But these are our decision variables in this problem. So we will do this simple model without some notation because it's a very small one. So let's say that x1 it's consumption of potato and x2 it's consumption of meat. These are decision variables. Parameters. Parameters, I already mentioned, these are basically all these numbers in problems that were provided, which are nutrition points, minimal budget of nutrition, or minimum amount of nutrition points to survive, budget in like financial budget, and the price of every product. I will not write it down again. Then let's first formulate the objective function. So object function. You can think a second about it, and when many students they say something more or less intuitive, they say that objective function is to maximize the consumption of nutrition points per day, or it's to maximize the consumption of potato and meat. This intuition, of course, it makes sense, but often we are required to read more precisely this actual description. And here we see that every citizen, what they really want, they want to consume as much meat as possible. So they want to consume meat, and of course, to consume it, they also need to survive. But their real aim is to maximize the consumption of meat, which we denote as x2. That's, I guess I need to write maximize x2. Another way how we could write down this thing, it's x maximize. X will. Now we have some constraints because they cannot consume the infinite amount of meat, unfortunately, even if they would be really happy. And when we read the description, so first constraint is to survive. So we need to consume products, meat and potato, but still survive. So we need to consume at least 20 nutrition points. Therefore, this will be the consumption constraint, and it said that our consumption, so consumption, should be more equal than 20, which are nutrition points. Now, how do we calculate the consumption of nutrition points? Nutrition points we can get from two resources, from potato and from meat. So the nutrition points that we get from potato, we calculate them as nutrition points per kilo of potato, 2 points, 2 and 5. So we get 2 points, 2 points per every kilo of potatoes that we consume, plus we get 5 points per every kilo of meat that we consume, and all this together should be more than 20 for us to survive. Then, of course, according to this objective function, maximize x2 and this constraint, we would happily consume infinite amount of meat. But we want to, unfortunately, we have the budget. And our budget, it says that we have 15 pounds. So money that we spend should be less than 15 pounds. And money spent, we again calculate them in a way. We spend them on x1 and x2, on potato and meat. And price of 1 kilo of potato is 1 and meat 5. So it's 1 and 5. These are all constraints that we have from the description. One more constraint is our standard non-negativity constraint. So we can write down as x1, x2 more than 0. And this is our problem. Now we need to find the optimal solution. So how much of the meat can we consume still to survive and under this limited budget? Here is the formulation of this model for Excel solver. I will not do it from scratch. You can see it in the solution. So everything is done exactly as we did before. We have the decision variables, which are consumption of both products, some parameters, which are nutrition value per kilo of every product and price, and then constraints. Constraints, as mentioned in the mathematical formulation, these are nutrition constraint and budget constraint. And we want to maximize the consumption of the meat, because second column or column B, it's for this in the objective function, it's basically equal to the consumption. So we can now start solver. All the data is already, all the objects are already referenced in the worksheet. So we have the objective. It's only meat. We want to maximize meat. To be consistent, we can basically put this reference in cell E7. Then, yes, we want to maximize it by changing variables C2, D2. Yes, these are our decision variables, and we have two constraints. Then, of course, consumption, it shouldn't be negative. It can be negative, and this is the linear model, so we use simplex. So let's solve it. The solver found the solution. Okay, let's keep it. So it said that under these requirements, under these constraints, we will consume 5 kilos of potato and 2 kilos of meat. Even so, we would maybe not like to consume potato at all, but we are forced. And this is the best what we can get to maximize our meat, but still to survive. Now, there is a tip here that, and in the textual description, that we are asked to experiment what will happen if potato starts to be more expensive. So, to check what happens when potato is more expensive and what decision maker will do, this Irish citizen, we increase the price of potato from 1 to 125. We increase it just by modifying the parameter. Now, if I go back to the solver, in the solver, I don't need to do anything because I didn't modify the model structure. I just modified the number, and all the parameters, they are already linked by the formulas dynamically. So let's remember that optimal solution now is 5 and 2. And when price of potato increases, let's solve it. You see that the increase of potato price under this condition leads to the increase of potato consumption to 666 and to the decrease of the meat consumption. And therefore, we see the increase in demand regardless of the increase in price, which is not that natural. You can think why it happened, but by this, we just finished exercise 3, in which we formulated the mathematical model, which looks like this, for this small funny example, and then we found the solution and experimented in it slightly in Excel solver. And this was it for the first tutorial. Next Monday, you can ask your questions during the question and answers session. So it will work in a way that I will start the question and answer session, and I will wait until like all questions are asked and I answered them. And if I don't get any questions, of course, I will not sit there for 3 hours. So yes, and also you can write your questions in the forum in Moodle, and if you have some questions which are related to your specific situation, drop us a message in email. Yes, so thank you for attention and have a nice weekend.